Good day, welcome to the video tutorial for General Chemistry 1, Activity Sheet, Quarter 4, MELC 3, Week 2, Electronic Structure of Atoms. Published by DepEd Region 6, Western Visayas. The topic today, Electronic Structure of Atoms, is a continuation of the previous lesson, Quantum Mechanical description of electrons. So we continue. The location of electrons in an atom can be predicted by applying three important rules: the Aufbau principle, Pauli's exclusion principle, and Hund's rule. Aufbau principle. Electrons enter orbitals of lowest energy first. Electrons are added one at a time to the lowest energy orbitals available until all the electrons of the atom have been accounted for. The last electron that enters an orbital is called the differentiating electron. It makes the configuration of an atom different from that of another atom. Below is the order in which atoms of levels are filled in an atom. We call this the mnemonic, which was already discussed on the previous video, Quantum Mechanical Description of Electron Part 2. So we will continue to Pauli's exclusion principle. It states that only two electrons can occupy the same orbital and two electrons must spin in opposite directions. When electrons with opposite spin occupy an orbital, the electrons are said to be paired. A single electron present in an orbital is said to be unpaired. Example, boron, which has an atomic number of 5 and has an electron configuration of 1s2, 2s2, 2p1. So here we have arrows represent the electrons, and the boxes, the orbitals. So for 1s2, there are two electrons, arrow up and arrow down. For 2s2, arrow up and arrow down. And for 2p1, arrow up. Remember that S has only one orbital and P has three orbitals. Okay, let's do more examples here. Hund's rule. When orbitals are of about the same energy, its orbital is filled with one electron with parallel spins before any of them is filled with the opposite spin electrons. For example, 5 electrons would occupy the p orbital of equal energy. The 3 electrons singly occupy first the orbital with aligned spin or the same direction. Arrow up, arrow up, arrow up. Or spin can be what? Clockwise or counterclockwise. The remaining 2 electrons must go into the p orbital as, okay? It will pair here on the first box and pair again on the second box. So that means the last electron that enters the orbital is this one here. So here we have some more example. Electron configurations of selected elements. So in this table we have column for element. Total electrons, which is also equal to the atomic number. Orbital diagram, you have to identify what is the orbital here: 1s, 2s, 2p, 3p, 3s, 3p, and then the electron configuration. So for helium or hydrogen first, we have the atomic number 1 and the total electron is also 1. The electron configuration is 1s1. So 1s here, so 1 electron, arrow up. For helium, total electrons 2. Electron configuration is 1s2. So, arrow up, arrow down. For nitrogen, 7. electron configuration is 1s2, 2s2, 2p3. So for 1s, there are 2 arrow up, arrow down, 2s, arrow up, arrow down. For 2p, it will enter the orbital first, fill it up in one direction. Arrow up, arrow up, arrow up. For oxygen, 8. 1s2, 2s2, 2p4. So for 1s we have 2. 1 arrow up, arrow down. For 2s, arrow up, arrow down. For 2p, arrow up, arrow up, arrow up. And then it will pair arrow down. Okay? For neon, 10. 1s2, 2s2, 2p, 6. So 1s, 2 electrons, arrow up, arrow down. For 2s, arrow up, arrow down. For 2p, arrow up, arrow up, arrow up, and then it will pair down, down, and down. Okay? For sodium, total electron is 11, or the atomic number is 11. Electron configuration is 1s2, 2s2, 2p6, 3s1. Remember that the power here, the numbers here, the exponent, if you add this up, it will be equal to the total electrons, or the atomic number. So 1s2, arrow up, arrow down. 2s2, arrow up, arrow down. For 2p6, arrow up, arrow up, arrow up, arrow down, arrow down, arrow down. And for 3s, arrow up. So the unpaired electrons here for sodium is 1. Okay? For silicon, 14. 1s2, 2s2, 2p6, 3s2, 3p2 is the electron configuration. So again, 1s is arrow up, arrow down. 2s, arrow up, arrow down. 2p, arrow up, arrow up, arrow up, arrow down, arrow down, arrow down. And 3s, arrow up, arrow down. And 3p, okay? 3p here, we have arrow up, arrow down. So this one is unfilled of electrons, this box. So there are 2 unpaired electrons. This is unfilled, empty. Chlorine has an atomic number of 17, electron configuration 1s2, 2s2, 2p6, 3s2, 3p5. 1s2, arrow up, arrow down. 2s2, arrow up, arrow down. 2p6, arrow up, arrow up, arrow up, and then pair, arrow down, arrow down, arrow down. For 3s, arrow up, then arrow down. For 3p, arrow up, arrow up, arrow up, and then it will pair on the first box, arrow down, second, arrow down. Okay? 1 unpaired electron. Okay, next. This is your first task. Activity 1, Table 1. Complete the table below by giving the atomic number, orbital diagram, and the electron configuration of the following given elements. Write your answers on your answer sheet. Okay, so you need to write down the total electrons, or the atomic number. Just open your periodic table, and on the upper left hand corner of the box, where the symbol of the element is your atomic number. Upper left hand corner of the box, it is a whole number. Okay, next, here is your periodic table. I guess you are very familiar with your periodic table. We need the periodic table to help us with another method to represent electron configuration by using abbreviated electron configuration, or the core method using the noble gases. The periodic table is divided into 2 periods, into 2 periods and groups. Periods is from left to right, left to right. That is rows, and groups is from top to bottom, or columns. Okay. So the Noble gases here are on this last column. Okay, the noble gases here are helium, neon, argon, krypton, xenon, radon, and oganesson. Okay, we will use this and use in making or doing this core method of abbreviated electron configuration. Okay, now the core method or noble gas configuration of an atom consists of the elemental symbol of the last noble gas prior to that atom, followed by the configuration of the remaining electrons. So for sodium, we make the substitution of neon for the 1s2, 2s2, 2p6 part of the configuration. So now it says here consists of the elemental symbol of the last noble gas prior to that atom. So for sodium, okay, let's start with sodium. Sodium here belongs to period 3. Okay, period 3. So the noble gas right after it or prior to it, the last noble gas prior to it is neon, which is in period 2. And for period 2, the noble gas that it will use is helium, which is in period 1. Okay, again. So for period 2, it will use helium as the core. Helium is in period 1. For period 3 elements, now from sodium to chlorine, it will use neon as the core because neon belongs to period 2. That means for period 3 elements, it will use neon that belongs to period 2. For period 4 elements from potassium to bromine, it will use argon as the core. Argon belongs to period 3. For period 5, rubidium 2, iodine, it will use krypton as a core. It belongs to period 4. That means a period before the element. It will use the noble gas that is before the period. Okay. For period 6, cesium 2, lanthanum to lutetium to hafnium to astatine. It will use xenon as the core. For period 7, 1, 2, 3, 4, 5, 6, 7, you just count downward. So this is period 1, period 2, period 3, period 4, period 5, period 6, period 7. So from francium to actinium to lawrencium to rutherfordium to tennessine, it will use or they will use radon or radon as a core. Okay, so let's try. For sodium, sodium is here. Okay, sodium is here. It has an atomic number of 11. It will use neon here. Okay, so sodium is in period 3. It will use neon, which is in period 2. Okay, now neon has an atomic number of 10. We will write the electron configuration. So for sodium, 1s2, 2s2, 2p6, that is already 10. But we need 11, so we will go to 3s2, but 3s2 is already 12, so we subtract it by 1. it becomes 3s1. So this will become 11 2 plus 2 4 plus 6 10 plus 1 11. Now, neon has an atomic number of 10. So the electron configuration would be 1s2, 2s2, 2p6, which is this one. 1s2, 2s2, 2p6, which is equal to this one. See? So that means that 1s2, 2s2, 2p6 is equal to the electron configuration of neon. So we could write here neon as a core and place it inside two brackets that will represent this 1s2, 2s2, 2p6. And what is left is 3s1, which is not included in the electron configuration of neon. So you just add here 3s1. That means sodium has an electron configuration that of neon plus 3s1. Okay, so that is the uh, abbreviated electron configuration of sodium. Okay, sodium is equal to neon bracket 3s1. Next example, selenium. Selenium has an atomic number of 34. Where is selenium? Here. Selenium belongs to period 4. So it will use what? Argon in period 3. That is prior or before. No? Selenium, that is the noble gas before selenium. So let's do this. Selenium has an atomic number or number of electrons of 34, and argon has an atomic number of 18. So what is the electron configuration of selenium? So 34. 1s2, 10, 18, 20, 10, 30, plus this 36. Okay? But selenium is only 34. So we subtract 2. It becomes 4p4, the electron configuration of selenium. Argon is 18. So 4, 10, 12, 18. Okay, so that is the electron configuration of argon. Look, this one here is equal to the electron configuration of argon. Okay, exactly the same. So that means that the electron configuration of selenium is that of argon here plus 4s2, 3d10, and 4p4. Understood? So remember that the symbol of the noble gas should be placed inside brackets. Okay, let's continue. Now, combining the core method and orbital diagram. So this table, we have the column for atom, electron configuration, abbreviated form, orbital diagram, and number of unpaired electrons. Okay, for sodium, we knew that sodium has this abbreviated form of Ne3S1, and selenium has an abbreviated symbol of AR for S2, 3D10, 4P, 4. So we have this 2 here. Okay? Now, the orbital diagram. Just write the orbital on top. So as we did earlier or so earlier, there are boxes. Okay? So this, you only need to do the orbital diagram of this remaining electron configuration here. So 3s in a box, there is only one, so arrow up. Number of unpaired electrons, 1. Okay? For selenium, now for S2, 3D10, 4P4, and look, there are no boxes here, but only pairs of arrows. So the box here class is was not used, but just an underline. The underline here shows one box. Okay, underline one box. Now So 4s. So the 4s is here. Now we labeled it. We labeled it. So arrow up, the red one, arrow down. For 3D, remember that we have this 4s has one orbital. The D has how many orbitals? One, two, three, four, five orbitals. And remember, P has three orbitals. So as D has five orbitals, we need also five underline here. Now, one, two, three, four, five. So the same as with P, D will also fill up the orbital, the electrons will fill up the d orbitals in one direction first before pairing. So the red one. Okay, so arrow up, arrow up, arrow up, arrow up, arrow up. There are 10. Huh? So we only have 5 there. So that means all these electrons will be paired. So down, pair, arrow down, pair, arrow down, pair, arrow down, pair, and arrow down, paired. So 1, 2, 3, 4, 5, 10. Remember 3d10. Okay, 3d10. And remember that each orbital can only hold 2 electrons with opposite spins. For 4p, there are 4 electrons. So arrow up, arrow up, arrow up, and then it will pair here. Arrow down. Number of unpaired electrons, 1, 2. Unpaired electrons. Now, you might get confused why there are boxes and why there are only underlines. Okay, so boxes is very clear, very you can easily identify now where is the 4s, the 3d, and the 4p, or the s, the d, and the p. Here, just be careful that when you have these orbitals, you need space in between, okay, so that it is easily identifiable and you have this label on top, okay, so that when it is uh, clear, it will be easy also for me to check your papers or your answer sheets. Now, next, electron configurations of a few elements do not conform to the Aufbau principle. This exception do not have any major chemical consequences, although they are interesting to know. The exceptions occur in the chromium and copper families. Using the Aufbau principle, you would expect the following electron configuration for chromium and copper. So, the difference here, class, is here at the end. 4s2 3d4, 4s2 3d9. But determined experimentally, the actual configurations are, okay, instead of 4s2, it becomes 4s1, 4s1, 3d5, 3d10. So the one electron here transferred on this one here, it's transferred here. So this arrangement is stable for chromium and copper atoms with only one electron in the 4s sublevel. Here we have some more examples. So please do it by yourself. And we have here the second task. Activity 2, table 2. Directions. Complete the table by filling in the abbreviated electron configurations and determine the number of unpaired electrons of the following given elements. Write your answers on your answer sheet. Okay, atom, electron configuration, orbital diagram, number of unpaired electrons. You can use the box or just the underlined orbital diagram. It's up to you. Okay, so the atoms here, the atomic number or the number of electrons is not provided. So just use your periodic table to get the atomic number or the number of total number of electrons. Okay. Next, reflection. Complete the statements below. This is the third thing, the third task that you will have to answer. I understand what, you don't understand what, you need more information about, so that I will know which one you understand, which one you do not understand, and which where you need more information. But for example, if you do not understand a portion or a part of this lesson, please ask in our group chat so that I can address it fast. Okay? So I hope that you have learned something. So if you learned something new from this lesson, please like and subscribe. If you already subscribed, it is greatly appreciated. Thank you so much. God bless and stay safe.